Okay, good afternoon. Let us start our lecture. So yesterday we talked about some special distributions for discrete random variables. Okay, so basically what we're interested is the number of successes in n dichotomous trials. So each trial supposed to be independent, and we have n trials, and for each trial there are only two possible outcomes, either a success or failure. Okay, that x is the random variable which denote the number of successes out of these n trials. Then we say that x follow a binomial distribution. So what you have to know is the following are the followings. So first of all, you have to know what x means. Okay, in this case, is x is the number of successes out of n independent dichotomous trials. Secondly, you have to know the form of the probability functions. So for binomial, there's a form, and it's valid only for x equal to 0, 1, 2, 3 up to n. And third, you have to know about the expectation of x as well as the variance of x. So usually these two, expectation of x and variance of x, are functions of some, we call it parameters, which are the constants that identify the distribution. So for binomial, there are two parameters. One is n. N is the number of observations, so number of trials, and p is the probability of a success in each trial. So we also talk about a negative binomial distribution. And a random variable, if it represents the number of trials. So this time the random variable is the number of trials. If the number of trials is x, we want to figure out how many trials do we need in order to get k successes, where k is fixed. All right. So unlike the binomial, so the role of number of successes and the number of trials are swapped in negative binomial. So you have to know what is the probability functions for negative binomial, and in fact for negative binomial, the random variable takes the values from k plus 1 up to infinity. So you also have to know what's the expectation of x and what is the variance of x. And there's a special case for a negative binomial distribution. The special case is when k equal to 1, which means that how many trials that we need in order to get the first successes. So we may just need one trial. What's the chance that I get one trial and then I got a success? Or I have to get 10 trials before I can get the success in the 10th trials. So this follow negative binomials. So today we also continue to talk about number of successes. Now this time the number of successes is not over an n trials, but instead it's over a certain interval. This interval can be time, can be distance. So we talk about the number of occurrence. So occurrence is considered a success. So we talk about the number of occurrence in an interval. This interval can be time, can be distance, and in fact, the interval can be extended to a region. All right. This is what we are going to talk about. All right, Poisson distribution. So here we start with an experiment that using a numerical values or random variable which represent the number of successes occurring during a given interval or a specified region. All right, and this we call it, in fact there's more than just this description for Poisson experiment. Okay, so we can have a given interval, time interval t, all right, or can be any length in minutes, day, week, month, or even a year. So that is a given interval. And we are also Poisson experiments might generate observations, okay, which can be represent the number of occurrence over this interval. So here is some example of the occurrence. For example, the number of telephone calls in an hour received by an office. So in this case, the interval that we are talking about is an hour. So over this hour, we want to know the number of occurrence or the number of calls comes in. All right? Or over a football season, so that may be a few months, all right? And the number of postponed games. So it's not the number of games, but number of postponed games. This is considered as random, all right? Whether a game is postponed or not, so it's random. So we want to know what's the number of postponed games over this football season. All right? But in fact, Poisson experiments of Poisson distribution can be applied to not just an interval, but to a region, all right? Or like an area or line segment or a volume or even a piece of material, all right? So it can be just a line, a part of a line, can be a part of a R square, or even part of a R cube or a volume. So for example, X may represent the number of mushrooms in a plot of land. So in this case, it's the area of land, all right? So we know the occurrence represents the mushroom. So we want to know how many, what's the number of mushrooms. And another example is for a given culture, the number of bacteria in this given culture. Or for a page, the number of typos in a page. So that is also can be modeled by a Poisson distribution. All right, so in fact, to be more strict, Poisson experiments consist of the following properties. First of all, the number of successes occurring in one time interval are independent to those occurring in other disjoint time interval or region of space. So in other words, if this is my interval, I divide it into sub-intervals. So the number of occurrence here over this interval is independent of how many occurrence in other intervals. All right? So, second, the probability of single success occurring, okay, for a very short interval. For a very short interval, all right, is proportional to the length of the interval. To the length of the interval. So, in other words, the probability of occurrence or a success here over this interval is proportional to the length. Let me call it delta t. So it's proportional to the length of this interval, provided it is very small, delta t, a small interval. All right, so here we have these two properties. One is for each interval, what happened to this interval, how many occurrence, how many success there in that interval should be independent of what happened to the others intervals. And secondly, a probability of one occurrence or one success, all right, is proportional to the length of the interval, provided the length is very small. There are other criteria. All right. The third one is that the probability of more than one successes occurring in such short interval is negligible. All right. So in other words, the probability of X or the number of successes, the more than two successes or more than one successes, negligible, which is almost equal to 0. Right. So it only applies to a very small interval. In other words, for this small interval, the occurrence is either 0 or 1. The chance that it has more than 1 is negligible. It's almost 0. So what does it mean? It means that basically for this interval, there are only two possible outcomes. Either you have one occurrence or no occurrence. All right. suppose we can have more than one, but here we assume that the chance is very small that you have more than one occurrence. Can we do such thing? Yes. Of course, if your interval is huge, then there may be more than one occurrence. But if I make it very small, is this small? If it's not small enough, I even make it smaller, so that the chance of occurrence in that particular subinterval is either 0 or 1, and have the chance of having 2 or more occurrence is almost 0. So it's like a dichotomous or like a binomial occurrence for within this subinterval. All right. So so this is the Poisson experiment. So a Poisson random variable is a random variable which, all right, have a PDF like this. For x equals 0, 1, 2, 3 up to infinity. So this one, the probability function is e to powers minus lambda. Lambda is the parameter, a constant that identifies the distribution. And then lambda to power x over x factorial. X factorial, recall it is x times x minus 1 up to 1. All right? And this holds for all the possible positive integers, including 0. This is always positive. All right? This is always greater or equal to 0 because lambda is positive, x factorial is positive, e to the power minus lambda is positive. Okay. All right. So what is e? E is the exponential. E is the natural logarithm. So we don't know the value, but it's approximately to be 2.1718, something like that. All right. Okay, so here shows the probability function for a Poisson distribution with different parameters. Now for a Poisson distribution, there are only one parameters. If you go back to look at this probability, this f of x, it's a function of three letters. One is e. E is just a constant. Lambda as well as x. X is in fact the value of this random variable. So lambda is the only constant that identifies different Poisson distribution. So so we usually write it as x follow a Poisson distribution with parameter lambda. All right, so if lambda equal to 1, all right, then this is the probability distribution. So you can see that the majority of the probability is concentrated on x equals 0, 1, or 2, while it's very small when x getting bigger and bigger. All right, so this is sort of like a right skewed, while when x equal to 4, then it is less right skewed or more symmetrical, while this is lambda equal to 9. So you can see that as lambda getting bigger and bigger, the Poisson distribution seems to be closer to a symmetric distribution. Don't forget, x, suppose take the value from 0 up to infinity. But the probability of for those x value which is large, the probability is very, very, very small, unless your lambda is very huge. Okay, so how does lambda, the parameter, related to expectation of x and variance of x? Or in other words, what is the expectation of x in terms of lambda, and what is the variance of x in terms of lambda? So it turns out that the expectation of x equal to lambda, and the variance of x is also equal to lambda. So what does it mean? Now if I go back to the graphs of the probability function, you can see lambda equal to 1. Lambda equal to 1. then you expect the x value is usually somewhere around 1. So you can see that it is 0, 1, and 2. But while if lambda equal to 4, you can see that the probability are more, the values are more concentrated around 3, 4, and 5. All right. While if lambda equal to 9, then the values are more concentrated around 9. So the expectation of x is equal to lambda. At the same time, the variance of x is also equal to lambda. So what does that mean? So you can see that, think of it. If lambda equal to 1, then the mean is close to it's somewhere takes the value which are small. Not only that, the variation is also very small. So the values of x basically concentrate around this region. But while for lambda equal 9, it means that the mean is 9. Not only that, the variance is 9. So that means it has a bigger spread or variation than with lambda equal to 1. All right, because the Poisson distribution, the expectation of variance, both are equal to lambda. All right. Okay, so here is a proof. So the proof is just to give you a chance to look at how we do the mathematics involving a Poisson or exponential distribution. So here, follow from the definition. This part is follow from the definition. It is x times the probability function, and then sum over all the x. Since for Poisson distribution, x take the value from 0 to infinity. So this is the definition. X times the probability function of x. Okay, so the rest is just mathematics. So how to do this one? So obviously x cancel the x with x factorial, so left with x minus 1 factorial. All right? And don't forget, this one you have to make some adjustment as well, because you cannot have 0 minus 1 factorial. So in other words, this one does not have x equal to 0. You cannot start with x equal to 0. In fact, x equal to 0 means this term is gone. All right? This one is okay with x equal to 0. So it's just e to the power minus lambda, lambda to the power 0 over 0 factorial, which is, so if I replace x equal to 0, then this is just equal to e to the power minus lambda. All right, because 0 factorial is 1. But once I multiply a 0, multiply to this e to the power lambda, so it's 0. So in other words, x equal to 0 for this term is 0. So we should start x equal to 1. So that makes sense. So after I do the cancellation, x don't cancel with x factorial. It's only cancel one of the factors. So you're left with x minus, x factorial means x times x minus 1 factorial. So you cancel the x, you still have x minus 1 factorial. So how to do the next step to simplify this one? So if you recall, so now I just rewrite this, take out one lambda. So this is x equal to 1 to infinity, e to the power minus lambda, lambda to the power x minus 1 over x minus 1 factorial. Now here is the trick. So this part. All right. Now this look like a probability function of a Poisson random variable. So what I just to do is to make it clear, I define y equal to x minus 1. So therefore, this one, it becomes e to the power minus lambda, lambda to the power y, and this is y factorial. But at the same time, you also have to do the limits of the summation. Where x equal to 1, y equals 0. So you have to sum y from 0, and when x is infinity, y is also infinity. So what can we say about this one? The sum of all this. This is equal to 1. Why? Because this part is basically is the probability function of a random variable y. And y follow a Poisson distribution with parameter lambda. And you are summing up over all the possible y value for a Poisson distribution. So it has to be 1. So it is equal to lambda. All right. So then how about variance of x? So we apply the same trick, but instead of working on expectation of x squared, we work on expectation of x times x minus 1. Now why I have to do that? Why I don't try to get expectation of x squared directly, but instead of working for x times x minus 1? The trick is because if you use x squared, you cannot do cancellation. But here I can write this x factorial as x times x minus 1 times x minus 2 factorial. So this x and x minus 1 cancel out. If you compute x squared, then you cannot do such cancellation. All right? So after that, you have this one. So now the question is to get this sum. So obviously, I can apply the same trick. So I take out lambda square. So I have e to the power minus lambda, lambda to the power x minus 2. All right? And this is x minus 2 factorial. X start from 2 to infinity. So now I change this to, let's say, y again. Y equal to x minus 2. Then this becomes like this. All right? So this equal to 1. So in other words, expectation of x times x minus 1 equal to lambda squared. But that's not what I want. I want to know what is expectation of x squared. But this equal to expectation of x squared minus expectation of x. All right? So this equal to, can I write it like that? All right? You can do it. You can write it like that. But you cannot write it like that. Huh? You cannot take out the square. You can only do the addition. So whether you do the addition first and then take the expectation, or you took the expectation first and then do the addition. All right? So these are changeable, but not multiplication. You cannot multiply x to x and then take expectation. This is not the same as taking the expectation first and then multiply the expectation of x to expectation of x. These are different. So this does not equal to this. Huh? So this is okay. So in other words, expectation of x times x minus 1 equal to lambda square, but this equal to expectation of x square minus expectation of x, which is lambda. So in other words, expectation of x square is equal to lambda square minus lambda. Expectation of x square is equal to lambda square minus lambda, at plus lambda. All right? So then obviously variance of x is equal to expectation of x square minus the square of the expectation, which is lambda square plus lambda minus lambda square. So cancel out, so left with lambda. All right? So that's what we have. So the variance of x is equal to lambda. All right. So the trick is, instead of finding expectation, okay, there are two things that you have to take note in the process of this proof. First of all, we make use of the sum of all the x of probability function equal to 1. In fact, you have to remember, okay? Summation e to the power minus lambda to the power x over x factorial, x from 0 to infinity, this is 1. In fact, after we have shown the expectation, I also know that if we have something like this, it doesn't matter whether it starts from 0 or starts from 1. All right? You can have x equal to 1. It's the same thing. What is this? The answer is lambda. All right? Okay. Then how about sum of x squared? E to the power minus lambda x over x factorial. x from 0 to infinity. This is the expectation of x squared, which we already proved that it is equal to lambda squared plus lambda. All right. So my point is that you have to remember, for any distribution, the sum of the probability function equal to 1. Sum of the expectation of x is equal to certain quantity. All right. So in Poisson, it's equal to lambda. All right. Yeah. So second thing is that you don't try to directly find the expectation of x squared, but instead we try to find the expectation of x times x minus 1. Why we have to do that? Because the probability function involves x factorial, which is x times x minus 1 times x minus 2 and so on. So we have to find the expectation of x times x minus 1. It's easier to work that way. All right, here is an example, some examples. So the average number of robberies in a day is 4 in a certain big city. Now, so in this case, so you have understand, it gives you a lot of the information. First of all, we are talking about the number of robberies, and then we are told what's the average, and it's for a particular city, big city, in a day. So you can think of it, we are talking about interval, a time interval, a day. All right? Interval. And we are talking about the number of occurrence. The occurrence is the robberies. All right? So on top, we also know the average. Average is 4. Okay? So we are asked, what is the probability that we have 6 robberies occurring in 2 days? All right? So how to deal with it? So basically, it's the number of occurrence. Okay, maybe we have x to represent the number of robberies. But this is not good enough. You have to specify number of occurrence, number of robberies, number of occurrence in a certain interval. So in this case, we are interested in 2 days. To be more specific, is in the city that we are talking about. All right, in that particular city that we are talking about. Okay, so the next question is, what is the distribution? So here we have an interval. The interval is a time interval of 2 days. All right, and we are basically asked the number of occurrence in this interval. So x follow a Poisson distribution. So the question is, what is lambda? If you remember, lambda means the average or the expectation, which means the average. So over 2 days, what is the average number of occurrence? So it will be 2 times 4. All right? Because in 1 day, we expect 4. So in 2 days, it should be 8. In 2 days, we expect 8 robberies. So the average is 8 robberies in 2 days. So x follow a Poisson with parameter 8. All right, so we are asked, what is the probability of x equal to 6? So that's what we're supposed to find. All right. So x follow a Poisson distribution, and probability of x equal to x is 0.122. So this is e to power lambda minus lambda to power x over x factorial. All right. In fact, we can have a okay. Now I don't have the table here. I just want to show you see whether I have tables. Okay, Poisson distribution. Okay, so this is a table. In fact, I uploaded for you. So this again, okay, it represents the Poisson probability. All right, Poisson, the word Poisson here, and it measures the upper tails. So that means each entries in the table represent the probability of the random variable x greater or equal to this value. So here, for example, this number represents the probability of x greater or equal to 4. Greater or equal to 4. While x follow a Poisson distribution with a parameter lambda equal to 8. Equal to 8. All right? So this just gives you some idea the right tail of the given probability. So probability of 6, so it's equal to this number, which is probability of x greater or equal to 6, minus probability of x greater or equal to 7. So we can get out this. All right? So it's equal to 0.122. This is for lambda equal to 8. Lambda equal to 8. All right, here's another example. So we have this average number of oil tanker arrive on a given day, or each day, a date is known to be 10. All right. So if x represents the number of oil tankers arriving, then if this is considered x, then x follow a Poisson distribution. Number of oil tankers arrival on a given day, then x follow a Poisson distribution with the average number being 10. So it's follow a lambda equal 10. So this is the distribution. All right. And the facility of the port can handle at most 15 tankers per day. All right. So what's the probability that on a given day, tankers have to be sent away? So in other words, we would like to find out what is the probability of x greater than 15, or probability of x greater or equal to 16. All right. So if the number of tankers arrive is less or equal to 15, then the port still can handle it. But if it is greater than 15, then we have problems. We have to turn them away. So we want to find out what is the chance that you turn away from the port. So we are asked to find this probability. So here is what I said. So you can add this. All right. If you don't have a calculator that gives you the CDF, then you have to work it out. So this one from 16 to infinity, there are infinite number of terms. So it's not a proper way. So we should get 1 minus probability of x less or equal to 15. So at least there are only 16 terms in this sum. This is the probability of x less or equal to 15. E to the power minus lambda, lambda to the power x over x factorial. All right? And so the answer is 0.0487. But you can also read out directly from the table. All right? Okay. Now, let me sidetrack a bit, ask you these questions. So you are given the average number of tankers visiting the port is 10. But how do I know it's 10? How do I find out the average number of all tankers? So if you are the employer of the port, then the boss asks you, hey, what's the probability that I turn away tankers? So you have to know how many tankers, average number of tankers arrive on a date. So what to do? So collect data, or you go back to trace your record. Yesterday, how many tankers arrived? Day before yesterday. Maybe you take the past month, look at all the 30 days, how many tankers arrived, and you take the average. So that is estimate of this average. I take the average of the past 30 days, or maybe more. Take the past year, 365 days. All right. So Maybe that's how you can estimate this number. But for this example, we are given this number. We don't worry about it. So we are told this number, so we just work out the probability. All right. So this is what we have. Okay, example 3. So in this example, we have a number of breakdowns. So this is the occurrence. Number of occurrence is over a period. And what is this period? This period is an 8-hour shift. So we are consider an 8-hour period. So over this period, the number of breakdowns, the number of occurrence. All right. So that should follow a Poisson distribution. And with a mean equal to 1.5. All right. So if x is the number of breakdown over this 8-hour shift, and then x follow a Poisson distribution with parameter 1.5. All right. So what is the probability of exactly 2 breakdowns during this midnight shift? Midnight shift is just as any 8-hour shift. All right. So what is the probability that fewer than 2 breakdowns during the afternoon shift? And what is the probability that no breakdowns during 3 consecutive 8-hour shift? All right. So so we do it one by one. All right. So let x represent the number of breakdowns per 8-hour shift. So x follow a Poisson distribution with parameter lambda, where lambda equal 1.5. And probability x equal to 2 is lambda to power x over times e to the power minus lambda over 2 factorial. So this is the answer. Then probability of fewer than 2 breakdowns. So in other words, fewer than, that means excluding 2. So it's x less than 2, which means that x takes 0 and x takes 1. And they're mutually exclusive, so therefore it's equal to x equals 0 plus probability x equal to 1. So it's 0.5578. Okay, the third question. We are asked to find out the probability of no breakdowns during 3 consecutive 8-hour shift. All right. Okay. So one way to do it is consider over one particular 8-hour shift, what's the chance x equals 0? So this is the probability. So, all right. Okay, there are 2. So obviously, for the next shift, the probability, so if x1 represent the number of breakdown in the first shift, 8-hour shift, x2 and x3. All right, so I just multiply this probability to this probability to this probability. So basically it's 0.2231 raised to power 3. All right. I'm asking what is the chance that 3 consecutive shift that have no occurrence, no breakdowns. So I work out x1 is the number of occurrence or number of breakdowns in the first shift, second shift, and third shift. And they're independent, so I just multiply all this. Each of them is equal to 0.2231. So the answer is 0.2231 raised to power 3. There's another way to look at it. So if we define a random variable x, all right, which is the number of 8-hour shift that experience no breakdown in the 3 hours shift. All right. So what y means is that, okay, we are looking at three time intervals. So for each one, it's either no breakdown or yes, there's breakdown. All right. So it's only 2 outcomes. So x can be considered as the binomial distribution with 3 trials. And each trial has a probability p. P is the probability of no breakdown. No breakdown. All right. So we are asked basically is probability of y equals 0. Y equals 0. All right? Yes? 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 What is independent? The machines operate across shift are independent. So that means what happened to one shift has nothing to do with another shift. Then, what is this? X. Right? Can X equal to 0 and equal to 1 at the same time? Can the number of breakdowns can be 0 and also the number of breakdowns for that particular shift, can it be 0 and 1 at the same time? No. So of course they're mutually exclusive. You confuse the two things. We're talking about X, which is the number of occurrence in a particular shift. While the independence is talking about the number of occurrence in different shifts. In different shifts. All right? So for this shift, I call it X. For the second shift, I can call it Y. So this X and Y are independent. All right? They operate differently. But whether X equal to 0, X equal to 1, X cannot equal to 0 and 1 at the same time. Right? X less than 2 means that X can be 0. I mean, we have to consider X equal to 0 and consider X equal to 1. And you have to add these two probability. This means that probability of X equal to 0, all right, or X equal to 1. Am I right? So this equal to probability of X equals 0 plus probability of X equal to 1 minus probability of X equals 0 and X equal to 1 at the same time. Is it possible? No. Number of occurrence cannot be 0, cannot be 1 at the same time. So this is 0. This is matrix. So it's just equal to the sum of these two probabilities. Right? Okay? So, okay. Thanks for asking. So please make sure that you understand when I talk about mutually exclusive, I'm talking about these two events, X equals 0 and X equal to 1. X equals 0 means the number of occurrence or number of breakdown in this particular shift equal to 0. And another one is when this number of occurrence equal to 1 for the same interval. It cannot be 0 and 1 at the same time. But you can have 0 occurrence, 0 breakdown for this shift and 1 occurrence, 1 breakdown for the next shift. Okay? You can have that. All right, so it work out when y equal. I'm sorry. Okay. So x equals 0. So y equals 3. We want all the 3. Sorry, y equals 3. So we want all the 3 shifts with no breakdown. So y equal to 3. All right. So it's 0.0111. Okay, example 4. So this time, we extend it to, instead of a time, we extend it to the area. So there's average one, quality controls, average 1 square foot of the door surface containing 0.5 minor fault. So fault is the occurrence. So we want to know, okay, how many faults, okay, over this door. And we know that for area of 1 square foot, there is 0.5 minor fault. All right. So in other words, here x is the number of minor faults. Okay, and we are talking about a certain area of the door. So we know that the average is 1 square foot, average is 0.5 minor fault over 1 square foot of the door surface. All right? So here is what the owner decides. So if there are 2 or more minor faults over the door, all right, then you have to rework. So in other words, we would like to find out what's the chance that a door will be reworked. And so we have to examine, all right, so a particular 1 square foot of the door, we look at it, see how many faults are there. All right. So what's the probability that the door will fail inspection and send back for reworking? And what's the probability that the door will pass the inspection? That means it don't have to rework. All right, so let X be the number of faults found in 1 square foot of the door surface. So X follow a Poisson distribution with the average equal to 0.5. So we send for repair is to get probability of X greater or equal to 2. The number of faults is greater or equal to 2, then we have to send for rework, which is equal to 1 minus probability X less than 2, so it's equal to 0.09. So in other words, based on this rule, whenever you inspect 1 square foot, you find out there are more than 2, greater or equal to 2. That means 2 or more faults, then you send back for rework. And the chance is 9%. That means 9% of the door will be sent back. All right. So if you are the manufacturer, you may think of control your quality, think of reduce this, so that in 1 square foot of the door, there may be 0.2 minor fault. Then in that case, the chance of send back for rework will be smaller. All right. Okay, so what's the chance that it passed the inspection? Pass the inspection means that the number of faults found is either 0 or 1, which is the complement event of probability X greater or equal to 2. So it's 0.9098. All right? Okay. So this is to link up the Poisson distribution and the binomial distribution. So far, we just discussed individual type of family of distribution. Now we try to link up the Poisson and binomial distribution. All right, here is a result. So this is a binomial random variable with parameter n and p. All right, so this is the probability function. Now, when n getting bigger and p getting smaller, all right, such that this n times p is considered as a constant as n goes to infinity, then x can be approximated by a Poisson distribution. So in other words, if x follow a binomial distribution with parameter n and p, and if n goes bigger and p getting smaller, all right, this is how mathematicians saying the fact that n is getting bigger until it reaches infinity, and then p is getting smaller and smaller until it reaches 0. But in practice, usually it's not that big, and this is not that small. All right. Okay, and so long as np is a constant, when n is getting bigger, all right. So then x can be approximated by a Poisson distribution with parameter np. So this becomes my lambda. All right? So that's the result. So in other words, they can prove that, but we don't bother. So this n factorial over r factorial n minus, this should be x. Choose x out of n. So this is n, this is x factorial. Px and q, or 1 minus p n minus x. So this expression, when n goes to infinity, this expression the limit is equal to this expression. All right. For those who are interested, you can search the Google. You can find a very simple proof for the limits. All right. So the idea is that for the probability function of a binomial distribution, think of it, when n getting bigger and bigger, so how to get n factorial is a huge number. All right. So so we show that when n getting bigger and bigger, p getting smaller and smaller, this is approximated by this expression. All right. So it helps us to find the probability of a binomial, a random variable. All right. So here is an example. Now in this case, suppose for an individual car having an accident at a junction with probability 0.0001, a very small p. All right. So if there are 1,000 cars passing through this junction on a given day, a period of a given day, all right, what's the chance that you have 2 or more accidents occurring during that period? Now, so x is the number of accidents. X is the number of accidents or number of cars involved in accidents out of 1,000 cars. All right? We're talking about 1,000 cars. So x basically follow a binomial distribution with n equal 1,000 and p equal 0.001. All right? So what we are asked here is the probability of 2 or more. So we are asked for this probability. All right, so you can use a calculator, use a program to do it. But now we also have another way to do it, is use the Poisson approximation. Gives you an approximate answer. So this one, since n is quite big, it's 1,000, and p is quite small, and the product is still okay. So x now can be approximated by a Poisson distribution with a parameter 1,000 times 0.001, which gives you, right, 1, 2, 3, so 0.1. So x can be considered approximately follow a Poisson distribution with an average equal to 0.1. All right. Expectation of x is n times p. All right. So that this expectation of x is used as the parameter. So this is lambda, which is expectation of x. All right. So in this example, n times p is 0.1. Okay. So here it is. So now this is how I got, if I want to find out the exact probability, or I use the above theorem, then this one is equal to, this is equal to 1 minus probability of x equals 0 and probability x equal to 1. So probability x equals 0, if you use the Poisson approximation, this is lambda to power x e to the power minus lambda divided by 0 factorial. So that's why it's e to the power minus 0.1. And this is equal to 0.1 to the power 1, e to the power minus 0.1 over 1 factorial. So it is, so this is the approximation. For this question, even we don't apply the approximation. So what is x equals 0? So it is 1,000 choose 0 over p. What is p? 0.0001 to power 0 times 0.9999 to power 1,000, right? This is probability of x equals 0 for a binomial distribution. Plus, continuous 0.0001 to power 1, and then 0.9999 to power 999, right? So it's still not that bad, all right? Provided that you can get 0.999 raised to power 1,000. All right. So what I mean is that you have to understand the link between binomial distribution and a Poisson distribution. So a Poisson distribution can be considered as a limiting case, or in other words, when n getting bigger for a binomial distribution and p is small, then this binomial distribution basically is similar to a Poisson distribution with a parameter equal to n times p. Okay, here's another example. All right, suppose that, all right, so these glass items have defects or bubbles. All right, so we know that on average 1 in 1,000 items produced has 1 or more bubbles. All right, so what's the probability that a random sample of 8,000 will yield fewer than 7 items having bubbles? So in other words, now we produce a glass panel. So there are holes, or not holes, bubbles, okay, or some defects. So we expect for each panel, the chance that it's being defective is 1 over 1,000. So it's a very small chance. So you expect 1,000 glass panel, there are only 1 have problems. So now we suppose have 8,000. So what is the chance that you will see 7 out of these 8,000 that have problems? So again, this is a binomial distribution, except that now the n is quite big. It is 8,000 and p is quite small. So we try to approximate this. So x be the number of items having bubbles, and x follow a binomial distribution with a parameter 8,000, all right, with p equal to 0.001. So n times p is 8. So therefore, you can consider x follow approximately Poisson distribution with parameter equal to 8. All right? So probability of x less than 7 means, so you can work this out from the statistical tables or from the computer program. Okay. So you can from the binomial table or this one again, obtained from a Poisson table. We don't have a binomial table with n equal to 8,000, so huge. But we have a table for a Poisson with parameter equal to 8, right? So this is Poisson. Okay, so if p is close to 1, we can still use the Poisson distribution as an approximate to a binomial distribution. Remember, I say x binomial n p. So n big, p small. But if p is close to 1, it's simply you just reverse the success and failure rule, then you will have the case p is getting small. All right, so you can still apply the Poisson distribution. The worst scenario is that p is somewhere around 0.5. It's not that small, not that close to 1. Then the approximation is not that good. All right, okay, so to summarize all the discussion on discrete distribution, we talk about discrete uniform distribution, we talk about Bernoulli distribution, and then binomial distribution. So you have to know what the random variable means, what is the probability function, what is the expectation, and what is the variance. We also talk about negative binomial, and as a special case, geometric distribution is a special case of the negative binomial. That means how many trials until I got the first success. Then we talk about Poisson distribution, all right? And also the link between Poisson and binomial. So binomial distribution, when your n getting bigger and bigger, your binomial distribution looks more like a Poisson distribution. All right, so now we move on, talk about some useful and commonly encountered continuous distribution. So again, the first one is uniform distribution. So what does it mean? It means that over a certain interval, A and B, between A and B, your density is uniform, which means that it does not matter what your x value is, they are the same. So you can see that the density function is equal to 1 over b minus a, which does not involve any x, which means that no matter what x you give, the probability density function will be the same, so long as x is between a and b. So beyond that, it's 0 otherwise. All right. Now, I think it's better to get a habit when we talk about probability function or probability density function is over the whole real line. That means all the x values. All right? But for continuous distribution, for this distribution, the density function will be 0 if your x is outside a and b. But if it's within a and b, it will take the form 1 over b minus a. All right, so this is the graph. In fact, unfortunately, I draw this line, but you can ignore this line. So basically, the PDF is just this part, and this part. All right. So in other words, when it is outside A and B, the PDF is 0. And for any x between A and B, then it is equal to 1 over b minus a. So that this area, now if this height is 1 over b minus a, in this example, a is 3 and b is 7. So this is 7 minus 3 or 1 over 4. This part is the length between this point and this point is 7 minus 3, so it's 4. So the width is 4, the height is 1/4, so the product is equal to 1. In other words, the area here is equal to 1. So sometimes continuous uniform distribution is to refer as the rectangular distribution. Rectangular distribution, because the PDF look like a rectangle. And what's the mean and what's the variance? So we can work it out. The mean is very simple. It's the average of the two endpoints, A and B. While the variance is the difference between B and A, you square it and then divide by 12. All right? So here's a simple proof, follow from a definition. Now, this one I skip one step. It should be from minus infinity to infinity f of x dx. Sorry, x times f of x dx. So this one divide into 3 integration. From minus infinity to a, it is 0. All right? And then from a, x times 0. From a to b, then it is x times 1 over b minus a. And then from b to infinity, again, it is 0. So it's like that. I just want you to remember, not to remember, to understand that expectation of x is integrate from minus infinity up to infinity, all right, over x times the PDF. All right? But it breaks down into 3 integration. This one is 0, this one is 0. Why? Because the integrand is 0 with the PDF equal to 0. So it left with this part, and the answer is a plus b over 2. All right, to find the variance of x, we find the expectation of x squared first, and it turns out that it's equal to 1 over b minus a times b cubed minus a cubed over 3. And this can be written as b minus a times a squared plus ab plus b squared. All right, so it's equal to this. And the variance is equal to the difference of expectation of x squared minus the square of the expectation, and it turns out to be like this, and I factorize it, so it becomes b minus a, the whole thing square, divided by 12. It's just a simple exercise to illustrate how to get the expectation of x and the variance of x for continuous random variables. Okay, here's an example. So suppose I want to choose a point, okay, over a line segment from 0 to 2. So what's the chance that this point lies between 1 and 3 halves? All right. So obviously, because I choose the point at random, so x is the location of the point from the starting point from 0. So this will be uniform 0, 2. So in other words, we are talking about, I try to fix a point. This x is the distance from 0. So here we are asked, the point lies between 1 and 1. 1 is here, and 3 halves is here. So what's the chance that x falls within this region? Okay, so what's the probability of x between, all right? So we have to do the integration. All right. So this is b minus a, so it's 2. So we do the integration, and after we complete, it's 1/4. So the chance that the point falls between 1 and 3 halves is 1/4. Of course, you can get the answer without doing the integration. You just look at uniform. So the width between covered by 1 and 3 halves is equal to 1/4 of between 0 and 2. So it is 1/4. Okay, here's another example. Try to find the CDF of this random variable. Now again, the CDF, when you find it, you should consider all the possible x value. That means from minus infinity up to infinity. All right? So by definition, the CDF for a continuous random variable is the probability of the random variable, right, less or equal to x. So it's equal to integrate, so you can consider like this. So this is my x. I'm looking at this probability, this area. So integrate from minus infinity up to x, and the PDF. All right. I don't want to write x here. Instead, I write t, so that you don't mix up these two numbers. If I put x here, it will be very confusing because they mean different things. So I change this to t. T is the argument used in for this integration. All right. So how to do the integration? It depends on the x value. So here it is. So we define it. If x is less than a, so you can think of it like this. So basically, it's like this, a and b. So PDF is 0 here, and then jump here, and then here. So now, for x less than a, so if x is here, what is the chance that what is the area over? So it is 0. So this one is integrate from minus infinity to x, 0. But then when x is here, then I have to separate the integration from minus infinity to x into 2 parts. From minus infinity up to a. Then stop here because the PDF is 0. Then from a to x, it is 1 over b minus a, when x is between a and b. But while if x is here, then I have to do to break down the integration into 3 integrations. From minus infinity to a, from a to b, and then from b to x. That means over here, one integration. Sorry, over here is one integration. Then this part is another integration, and this is the third part of the integration. All right. So, but this whole thing equal to 1. So this is the answer. All right. So when x is between a and b, the CDF is x minus a over b minus a. So it's quite obvious, right? If this is a, this is b, and this is the PDF. So if x is here, basically the area is this part, which is x minus a, the length. X minus a is this part, times this is b minus a, right? So x minus a is the width, all right? X minus a times b minus a, all right? And the whole thing, okay, is 1 over b minus a. My mistake. 1 over b minus, the height is 1 over b minus a. So you multiply, this is the area. So this is the area. X minus a over b minus a. But while if your x is here, then the area will include the whole thing. So that's why it's 1. All right. But if x is here, you don't have any area. So it's 0. So the CDF here is defined for all the x value. X less than a, x between a and b, and x bigger than b. So defined over the whole real line. All right? Okay. Next distribution is very interesting distribution called exponential distribution. First of all right, we say that x follow exponential distribution if the probability density function is given in this form. So the parameter is alpha, exponential alpha. All right, when x is positive and 0 otherwise. So we can show that integrate from minus infinity to infinity of the f of x equal to 1. And here is 2 examples, 2 particular exponential distribution. This one with a deep drop here is exponential with parameter 4. While this one is the exponential, the PDF of exponential distribution with parameter 1. All right? So how does the expectation of x link to alpha? So it turns out that expectation of x equal to 1 over alpha. And the variance of x is 1 over alpha squared. Is it next slide? Yes. Here. All right. So, okay. So here again, just to illustrate how this method, how can prove that. So follow from a definition is integrate from minus infinity to infinity f of x dx, which break down to minus infinity to 0, 0 dx plus 0 to infinity. All right. Oh, sorry, we're talking about expectation. So multiply x times alpha e to the power minus alpha x dx. So this part is 0, so you just have to work on this part. So differentiate this will give you this part. All right? These two are the same. Differentiate minus e to the power minus alpha x with respect to x. That will give you alpha e to the power minus alpha x, which is the one here. All right? So then we apply the integration by parts. Integration by parts. Names is not important. Basically it's saying that integrate u of x dv of x is equal to uv minus integrate v du. So this is my u of x, this is my v. So it's equal to u times v. Evaluate at 0 to x from 0 to infinity, then minus integrate. So this is uv, this is v du. This is u dv. All right? Integrate u dv equal to uv minus integrate v du. All right? Okay, so once we substitute 0 here, so it's 0, substitute infinity here, this part is 0. So basically this is 0 minus 0, and we just have to work on this one. So minus become plus. So we just work on this part. All right? So this is equal to 1 over alpha. All right? But if you remember, I mentioned you can make use of the properties of integrating PDF equal to 1. So this one, you just have to write alpha and 1 minus alpha. This is the PDF of an exponential distribution. Integrate from 0 to infinity, this should equal to 1. Therefore, the answer is 1 over alpha. So after you learn your probability, all right, so you can make use of these properties of probability function or probability density function to do your integration easily. Okay, so now add one more to your arsenal. Integrate x alpha e to the power minus alpha x dx. This is from 0 to infinity. This equal to 1 over alpha. Because we just work out the expectation is equal to 1 over alpha. All right? Okay, so expectation of x squared. So I just repeat what I follow the same step. U dv, so it's uv and integrate v du. All right? And finally, after I simplify, I got this part. Immediately, I know that the answer for this one. What is this? This is nothing but just expectation of x, where x follow an exponential distribution with parameter alpha. So therefore, this is equal to 1 over alpha. So it's 1 over alpha. All right? So it becomes very neat. So the answer is 2 over alpha squared. So therefore, what's the variance? The variance equal expectation of x squared minus the square of the expectation. So it's equal to 1 over alpha squared. Okay? Now, sometimes people will write this as, instead of alpha e to the power minus alpha x, they will write it as 1 over mu e to the power minus x over mu. If you represent the density function like that, then expectation of x is equal to mu. So you have to, I mean the form may be different, but basically the same. If I use the PDF in the form of alpha e to the power minus alpha x, then the expectation is 1 over alpha. But if I used, I use it, the PDF in terms of the expectation of x, which is mu, then the PDF is 1 over mu e to the power minus x over mu, where mu is the expectation of x. All right? Okay. Now, this is a very interesting property. It's called memorous properties. What it means, basically, it's like this. This is what we call memorous. Okay, this probability means what? Means that, okay, if I know that x is bigger than t, then what is the chance that x bigger than s plus t? It turns out that it's the same as the chance of x bigger than t. Or in fact, x, the exponential distribution, is very commonly used to model the survival time or the time to failure. All right? So that means the chance that an item fails at the beginning should be very exponential distribution. All right? So or survives. X survives. All right? Should be very high at the beginning, but then it's getting lower and lower. Now, what it means here is that it doesn't matter what happened in the past. All right? So in other words, okay, I start from here, and then I survive. I know that x is bigger than s. All right, this is s. And then what's the chance that I will survive from s plus t? All right? It's the same as I start this as a starting point. So it's the same as the chance that I will start x bigger than t. Okay? So what I mean is, I start from 0. So I get through s. So I know that, okay, I already reached here. X is already bigger than, x is bigger than s, so I reach here. So what's the chance that, knowing that I'm here, So what's the chance that x is bigger than s plus t? So now what this result saying that, okay, the chance is the same as if you start fresh. Consider this as 0, okay? To look at it as t, okay? X greater than t, all right? So in other words, I don't care whether you have survived the t or not. So everything starts fresh, all right? So that's what we call memorized properties, all right? Not too many distributions have these properties. For other distribution, this is not true, all right? So here, we can prove it easily, all right? So for this part, all right, x greater than s plus t and x greater than s. So this is event A given event B. So it's A intercept B, all right? So it's equal to probability of x, So this is A intercept B divided by probability of B. So this is probability of B. All right? Now, but between A and you can see that, all right? A basically, A is a subset of B, right? If x is bigger than s plus t, then x must be bigger than s. So in other words, this is true, right? So x bigger than s plus t, then of course x is bigger than s. So A is a subset of B. So if A is a subset of B, what is A intercept B? It must be equal to A, right? Am I right? If A, okay, probably A intercept B, okay, but A is a subset of B, therefore A intercept B, you think of it, A, this is B, and A is inside. So A intercept B must be equal to this A, right? So it's equal to probability of A over probability B. And of course, you just do the integration, integrate from s plus t to infinity, the PDF, and this is s to infinity. So it turns out to be, after you do the integration, is like this. And you can cancel out, so this is e to power minus alpha t, which is probability of x greater than t. All right? So you can think of it like this. Waiting time, for example, waiting a bus. So I go there, I already wait for 5 minutes. No bus coming. Okay, so I've already waited for 5 minutes. All right. So now you ask, okay, I know that I wait for 5 minutes. So what's the chance that I have to wait longer than 10 minutes or longer than 9 minutes? Add additional 4 minutes. So this memorized property is saying that, okay, forget about you have been waiting for 5 minutes. So it's the same as I just arrived, wait for another 4 minutes. It's the same chance. So that's the memorized. Forget about the past. You don't need the knowledge of the past. So whether it is bigger, so I already survived, I already wait for S minutes, so what's the chance I wait an additional 10 minutes? So it's the same as, okay, forget about you wait for S minutes. So it's the same as you wait for another T minutes. So that's what the whole theorem say. All right? So that's memorized properties. So this is how you got the integration. So only exponential distribution has this nice, I cannot say nice properties, but has these properties. I mean the past will not have impact. You can forget about it. Right. So no memory in the sense that, okay, let's say x is the life length, all right? Then if the light bulb survived S time units, all right, then what's the chance that it survives the next T units? So it's the same as you start fresh. from this point onward, how long what's the chance that it will last another t units? Not another, last t units. So that's what it means. All right. So here it say that, okay, given that it lasts s minutes or s units time, then what's the chance that it lasts another t? So this is what I want to find out. And now it's saying that, okay, forget about your s. It's the same as just last for t units. So these two probabilities are the same. So that's what the memorized property is saying. All right, so find the CDF. We have already done this one. So just to integrate, so the CDF turned out to be 1 minus e to the power minus alpha x. All right. And again, I say x greater or equal to 0. So how about x? X less than 0. Sorry. So for x less than 0, f of x is equal to 0. Because the PDF is like this. It's 0 here and then drop here. So the area, if this is my x, I'm basically looking at this area. So if x is here, then there's no area. All right, so the CDF is 0. All right, so the probability of x greater than little x is e to the power minus alpha x. All right, just 1 minus this quantity. So give you this. Only for x greater than 0. Okay. Suppose the failure time of a system follow exponential distribution with a mean equal to 5. All right, 5 years. So what's the probability that at least 2 out of 5 of this system are still functioning at the end of 8 years? Now this example consists of 2 parts. First of all, it consists of random variable t, which is the failure time. So t follow an exponential distribution with parameter mean is 5. So it's 1 over 5. All right? And the second one is number, let me call it x. X equal to the number of systems. All right? Out of x. Number of systems out of 5, sorry. 5 systems that have something to occur. What is this? This is to function, still function after 8 years. So still function after 8 years. All right? So x is the number of items or system out of 5 systems that is still a success. And what is considered success? Success is still function at the end of 8 years. That means the lifetime is more than 8 years. All right? So you have to figure out, okay, so this one, basically x will follow a binomial distribution with n equal to 5, and p. P is the probability that it survives more than 8 years. So here it is. So t follow exponential with 1, 5. And the probability that it lasts for 8 years or more is approximately equal to 0.2. All right. So I just make it nice. If you want exact, you can write down the exact up to 4 decimal place. All right. But I just make it rounded to 0.2. All right. Then x is the number of system out of 5 that survive 8 years. Now this one, x is modeled by binomial. Why? Because basically we're interested in the number of success. A system is either lasts more than 8 years or less than 8 years. So it's a failure or success. So we consider the point lasts for more than 8 years is 0.2. So we are asked to find probability x greater or equal to 2. All right, so the answer is 0.2827. So this is how you get the binomial distribution. So another example, all right, so here we have this response time to a certain inquiry. So follow exponential distribution with expect response time is 5 seconds. So find the probability that the response time is at most 10 seconds. And find the probability that it's between 5 and 10. So it's quite straightforward. So x follow exponential, and you have to work out the parameters, which is supposed to be 1 over expectation of x. So in this case, we are told that the average is 5. All right, so it's 1 over 5. All right. Oh, there's no p, right? So it's just equal to 5. So now we make use of what we just learned. F of x equal to 1 minus e to the power minus alpha 1 over 5 times x. All right, it should be alpha, and the alpha equal to 1 over 5. All right, so we just substitute x equal to 10 and get this form. So it's 0.86. So the response time should be less or equal to 10 with a probability equal to 0.86. So between 5 and 10, so we just work it out. So it's equal to, this is the answer, 0.23. All right, so it's quite standard way to do things. But you have to figure out what x means and also what is the expectation or how it links to the parameters, because you need to know the parameter in order to compute the probabilities. Of course, the other one is to convert your question into a probability statement involve the random variable x. So what is the x value? So in this case, first part is x less or equal to 10. Second one is x between 5 and 10. So x exponential distribution is to between occurrence of two successful events. All right. So that is another way to look at it. The time between two, you can think of it because this is one occurrence, this is another occurrence. So this time for the next occurrence can be considered using the exponential distribution. All right. So it's quite natural. So basically, the time between two successful occurrence means that I look at from this occurrence, look at how long it takes for the next occurrence. That means how long it takes for the occurrence. All right, so it's followed by, it can be used, you can use the exponential distribution to model it. All right, so I think I stopped here. And yeah. So I've already uploaded tutorial 7. So you can work on tutorial 7 after your test. All right, yeah. This evening you have midterm test. All right. Multipurpose sports hall 2. Okay, so since I see you here, I also see you in the midterm test. And for those who have not watched webcast, okay, so just you already attend your test when you web.